In this episode, a record-breaking super tower.
As a Londoner, even during the building process, it was already an icon on the skyline. This really is an engineering marvel.
Taking structural design to new heights.
Look at the crazy amount of glass that this building uses. 11,000 separate pieces. What a stunning sight.
And the pioneering historic innovations.
It was the huge power that meant that previously unimaginable weights could be lifted, and it opened up a whole new frontier.
That made the impossible possible. London. Home to a skyline that boasts some of the world's most iconic buildings. But in 2012, a modern marvel altered this historic vista forever. Two superfans, physicist Andrew Steele and engineer David Knight, are checking out this supersized structure from two equally impressive viewpoints. David, the way most of the city's 8 million residents do, from the capital's streets. And Andrew, with a view normally reserved for the birds.
Wow, look at that. It looks like a piece of crystal, a splinter coming up through the earth.
Soaring to 309.6 metres, the Shard is London's tallest tower.
It's so tall and it's such a prominent part of the skyline that you can't help but notice it.
That's an incredibly audacious piece of architecture and some very impressive engineering.
The Shard's jaw-dropping height is down to owner Irvine Seller's huge ambition and architect Renzo Piano's inspired vision. But it was also born of necessity.
Looking across the London skyline as we approach from the south, you can really see it's just crowded. There's buildings everywhere.
Building in that tight space is a very, very difficult task.
We've got the whole city on our left-hand side now, the Gherkin, the walkie-talkie. We've got all these different buildings crammed into such a tiny space.
In this dense urban environment, the engineering solution to packing massive floor space onto a relatively tiny footprint was to build Western Europe's tallest skyscraper.
Irvine Seller had a dream of building a tall building, a vertical city, and this is the result.
Situated in one of London's busiest commuter hotspots, the jaw-dropping 309.6 metre tower is over 3 times the height of Big Ben. The unique pyramidal façade is made of a staggering 11,000 glass panels, enough to cover 130 basketball courts. Beneath the 60-metre spire lies the spine of the building, a colossal concrete core providing the backbone for 72 habitable levels with over 100,000 square metres of floor space. In 2009, construction on this immense scale posed a career-defining challenge for engineer and project director John Parker.
Building these buildings is always exciting. You're building up taller than anybody's gone in Europe, but this one was particularly difficult.
The dense urban environment would push the team to its limits.
It's in this congested site, just in the corner of a railway station, things going on all the way around it. We had no spare site in which to build it.
It's smack in the centre of London, with London Bridge Station on one side, Guy's Hospital Tower on the other, the Jubilee line of the tube passing very close underneath. And to add to all of that complexity, there was a building already on this site that needed to be removed before construction could begin.
Removing the former tower's 25,000-ton weight could make the site impractical.
When you put a building on the ground, the very heavy weight compresses the soil. It's like a sponge. It creates a divot where the building is. And when you take that weight off, the ground wants to heave, wants to respond and go back to where it was originally. And time is of the essence. You want to put the weight back onto that ground as quickly as you can.
So how do you construct the tallest tower in Western Europe at speed? And in one of the most sensitive sites in central London. This incredible engineering feat may not have been possible without a great innovation from the past. When it comes to building up, man has always defied the odds.
Well done.
In the deserts of Jordan, the sculptors of ancient Petra carved its vast buildings out of sandstone cliffs, while safely perched on a series of giant stone steps.
Sorry.
Although masonry buildings were rare in Italy's 12th century Bologna, warring noble families looking to build their prestige erected over 100 towers in a city where bigger was definitely better.
Mamma mia, what a whopper.
Perhaps the first skyscraper city was 16th century Shibam in Yemen. Adopting ancient techniques, its engineers used mud bricks to build high-rises that were so impressive, it's known as the Manhattan of the desert. But building these high-rise masterpieces for the modern metropolis would require some subterranean genius. In the 1950s, the bustling Italian city of Milan wanted to build an underground railway system, but was facing two apparently insurmountable challenges. Firstly, large-scale excavations would cause chaos, as engineer Luke Bisbee has come to see for himself.
We've come here to a site where the metro network is being expanded. And being here and seeing the scale of this site, you can imagine the tremendous disruption that would be caused if you tried to do this in the center of the city. Really an enormous challenge.
Poor soil conditions below ground also made tunneling beneath the city streets impractical.
This is actually a really good illustration of one of the key problems here in Milan. We're down here at the bottom of the excavation, and you can see this is an area where they're just getting ready to start to dig a tunnel. And the engineers have gone to really heroic efforts there. Around that wall, you can see they've put some rubber gasket, and they've really tried to keep the water out of the site. But in spite of that, you can see how much water is still flowing in. So these are about the worst conditions you could hope to be digging tunnels in.
It was down to brilliant engineer Dr. Christian Vader to find a solution. The traditional method of creating a relatively shallow tunnel was known as cut and cover.
Let's imagine that I want to dig a trench down between these buildings. And you can see what happens when I do that in this sandy soil. Initially, there's no problem. But if I push just a little bit too far, you can see that eventually I destabilize the soil and my structures will fall into the trench. And obviously that's completely unacceptable on a site in a congested urban center.
To avoid the risk of subsidence and to keep the city moving, Vader turned the idea on its head.
Instead of building one big trench initially, he built two little trenches down the sides of the buildings, and into those trenches he inserted reinforced concrete walls. And these then became known as diaphragm walls.
Vader then built the roof of the tunnel so that the city traffic could resume above, whilst underneath, in the stabilized environment, digging, tunneling, and construction could continue. Instead of cut and cover, Vader's technique covered, then cut. Now known as top-down, this method was adapted all around the world as a way of completing major subterranean projects with significantly less interruption to the world above.
So what Vader achieved here in Milan was to pioneer a really innovative construction method. And it's fair to say that standing down here in one of the new tunnels of the Milan Metro, it simply wouldn't exist without that construction technique.
2009, engineers at the Shard were faced with a potentially challenging site and a pressurized construction schedule.
As soon as a project like this starts, you're against the clock every second of the day. Time is money. You need to keep going and keep going quickly.
The solution for engineer John Parker and his team was to build on Milan's innovative underground methods with the added twist of building up.
Normally a building like this would be built by building the basement first and digging a big hole down to the bottom level of the basement, and then starting the core from that lowest level and building upwards. Now we built the core on stilts effectively that held up the core while we were building it upwards, and then we were at the same time digging underneath it and going downwards. That had never been done before. It was an innovation for the Shard.
Incredibly, just 23 of the building's piles would support the structure's central concrete core as it rose from a void in basement level 2. As excavations and casting of the underground floors continued around the pre-sunk columns, the core rose as if balanced on a tabletop above.
This allowed the engineers to shave literally months off this project, and the Shard was built much more quickly and much more cheaply than it could otherwise have been. This really is an engineering marvel.
This audacious twin-pronged approach was an unprecedented achievement. But to complete this super tower, engineers faced more challenges and would have to turn to another of history's great innovations.
The technique that Hagelin developed for this cylindrical shape was absolutely revolutionary for its time.
To produce more impossible engineering. At nearly 310 meters, the Shard is the tallest tower in Western Europe. And today, superfan and engineer David Knight is taking in its jaw-dropping scale from the street. While fellow enthusiast physicist Andrew Steele is getting a privileged bird's-eye view of the already iconic tower.
The Shard is an incredible building. It just stands high, proud above the London skyline. And this incredible bit of architecture really does put London on the map.
This is a really radical building. It imposes on the London skyline like nothing else. It ascends into the air and the whole thing shines and glistens in the sun. What a stunning sight.
With its luxury apartments, hotel, and 55,000 square meters of office space, this 87-story engineering marvel has set a new benchmark in skyscraper design. But this huge ambition comes at a price. During construction, the £430 million project would require more than 1,400 workers on site. With such high stakes, as engineers tackled the complex concrete core, they couldn't afford to let the schedule slip.
The slow bit of construction is building a concrete core that is the real basis of stability for the structure. It holds the building up, holds the building solid against wind loads, and is a very, very important part of the building. Getting that in place quickly is a real challenge.
And with the central column expected to consume over 10,000 cubic meters of concrete, how do you construct it in record-breaking time? This may not have been possible without a groundbreaking method pioneered in the past. Architectural historian Jen Mason-Garb is in Minneapolis in the USA to find out how an innovation built to satisfy a nation's love of baking ultimately influenced construction methods around the globe.
In the 1880s, Minneapolis was known as the flour capital of the world. Raw grain was brought here from across the northern prairie, processed here, and then shipped across the country and around the world.
But the industry was not without risk. Dry millstones could ignite flour dust, causing catastrophic explosions within the wooden silos. In 1878, the Washburn A, one of the largest mills in the city, was destroyed with the loss of 18 lives.
Grain merchants were facing a storage problem, so clearly a new solution was needed.
The answer would come from a partnership between engineer Charles Hagelin and grain trader Frank Peavy, who together set out to design a more resilient silo with an experimental prototype.
So this is what they constructed, the world's first reinforced concrete grain silo. The technique that Hagelin developed for this cylindrical shape was absolutely revolutionary for its time.
Hagelin designed a wooden cylindrical mould and filled it with concrete. Once the concrete had set, the mould was removed and placed on top of the first section. This process was then repeated until the desired height was reached. Many didn't believe that concrete would hold the volume of grain without collapsing. But when complete, the experimental tower was filled and tested.
So Peavy and Hagelin's experiment worked. They had solved the grain storage problem, and they could take what they learned here and use it all over the state.
Spurred on by their pioneering concept, the result in 1908 was the newly built Washburn-Crosby Elevator 1, part of the Washburn A mill, which at its peak produced over 900,000 kilograms of flour every day.
The most innovative thing about the design are these 15 cylindrical silos, each measuring about 100 feet tall. Constructed by Charles Hagelin, they were the first large-scale concrete grain silos in the US.
To construct the silos, Hagelin built on this sectional prototype, adopting an ingenious new method called slip forming, a technique that allowed him to continually move a concrete-filled mould.
So what we've got here is a simple demonstration of how slip forming works. I've got this bucket of slightly wet sand here. This is going to represent our concrete. And I've got this other bucket here with a hole cut in the top. This is going to represent our slip form. And here's how the process works. A little of the concrete goes in, and slowly, about a few inches every hour, the slip form gets raised up and up. And then I add a little more, and raised up a little bit higher.
To reduce the joins and so increase the strength, the rig was continually forced up by hydraulic jacks, whilst the concrete was poured non-stop. It meant that, while the concrete at the top remained wet and fluid, by the time it emerged from the bottom of the moving mould, it had dried enough to be capable of supporting the growing structure above.
The combination of the speed of the rig, how fast the slip forming moves up the structure, and the fact that the concrete has to be poured continuously into the top so that the top layer never fully cures, this is the key to making this whole process work.
The operation was so efficient, it could scale 2.5 meters in just 24 hours, completing a cylinder in around 12 days.
Hagelin's use of slip-form construction revolutionized the way that tall buildings are constructed. And today, concrete has become one of the most widely used materials in construction, allowing us to build higher and faster than ever.
Nearly 8 times higher than the Washburn-Crosby elevator silos, the Shard's concrete core would measure 1/4 kilometre. And to construct it at speed, engineers needed a supersized solution. A giant slip-form rig measuring 26 by 22 metres.
It was moving upwards at 3 metres a day, almost a floor a day. You have steel shutters which form the shape of the concrete, and then they're moved up almost continuously, 6 days a week, 24 hours a day.
Fed by a high-capacity concrete pump, the system was so efficient it reached the 21st floor in just 10 weeks.
It's amazing to think the first 21 stories of this concrete structure went up before they'd even finished the foundations below.
Still perched on just 23 piles in the centre of the basement, before the core could continue its journey to the 75th floor, it needed more substantial support. This would involve creating basement level 3's colossal raft foundation, and the UK's largest ever single concrete pour.
It took 32 hours. We poured the whole thing in one go. It's as much as 3 metres thick in the middle, underneath the core, and it was 5,500 cubic metres of concrete. They had trucks coming in from 3 different concrete plants. It was tremendously exciting to see all that concrete arriving on site.
But completing this mammoth structure would require further innovative solutions from the past.
How do you put that fire out if there's nobody around?
To produce more impossible engineering. In 2012, London's skyline was transformed. As tall as 70 double-decker buses, the Shard dwarfs everything around it. And today, 2 of its biggest fans, physicist Andrew Steele and engineer David Knight, are taking in this game-changing architectural masterpiece from every angle.
This is London's Burj Khalifa, this is London's Shanghai Tower. It was built in very trying circumstances and at speed, and London engineers are really proud of that achievement.
Built from a central concrete core, the tower's unique hybrid superstructure is pulled up around it. 40 floors constructed of steel, 29 stories of concrete, topped off by a monumental 23-storey spire at the pinnacle of the building. With his bird's-eye view, Dr. Andrew Steele is under no illusion as to the construction problems posed by the tower's immense height.
When you're building a tower that's over 300 metres high, one of the real challenges is getting the people and the materials up to these incredible heights when you're doing the construction. And the higher the tower gets, the harder that challenge becomes.
Construction had never been attempted before at a building this tall in central London, and it was a real challenge to get men and materials up to the top floor.
So how do you manoeuvre such enormous loads in such a challenging environment? This gargantuan task may have been impossible without another inspired innovator from the past. To construct their colossal pyramids, the ancient Egyptians had to rely on elbow grease and a lot of determination to scale their network of ramps. As cranes were introduced, the treadwheel allowed engineers to use leg power with impressive results.
Faster, faster.
Although only walking pace was recommended. Erecting a giant obelisk in 16th century Rome required more muscle. It would take 800 men to raise a vast lifting tower. Plenty of power to get it up, as long as no one let you down.
Oh dear.
A more reliable solution to heavyweight hoisting would come 3 centuries later. Dr. Rhys Morgan is taking to the waterways of Venice to discover how a seafaring tradition ultimately led to a unique engineering innovation.
Throughout history, this city has had an unshakable affiliation with all things waterborne, and the mid to late 19th century was no different. It was a time of great change in the maritime industry, and old wooden galleys propelled by oar and wind were being replaced by steel-hulled ships and great big engines.
This new wave of heavyweight construction would pose a huge problem for engineers at Venice's historic naval shipyard, the Arsenale. Traditional manually operated cranes weren't adequate for increasingly heavy loads, seriously compromising the Italian Navy's ambitious boat-building program. They turned to brilliant British engineer Sir William Armstrong. His groundbreaking innovation, developed in the dockyards of Newcastle in the UK, would offer the perfect solution to Venice's maritime construction conundrum.
Because of the growing trend of metal hull construction, the Navy decided to commission just the thing for the Arsenale. And here it is. The stunning Armstrong crane.
Completed in 1885, the colossal structure was an imposing addition to the Venetian skyline. And today, Rees has unique access to its equally impressive historic inner workings.
And the way it works is like this. This huge boiler would generate enormous amounts of steam, and that steam would flow up through the pipework down into these chambers below. The steam drove these enormous pistons back and forth, and they in turn helped pressurize the hydraulic circuit. The water was taken from the lagoon outside, and the pressure from the pistons generated huge amounts of pressure on the hydraulic system itself.
Capable of lifting an unimaginable 160-ton load, the heavy-duty crane transformed the fortunes of the Arsenale.
It was the power that meant that previously unimaginable weights could be lifted, and it opened up a whole new frontier in crane technology.
Over a 30-year period, 9 more of Armstrong's cranes would be installed around the world, heralding a new era in crane development.
By pushing the boundaries of what cranes were capable of, Armstrong created a landmark in engineering history and paved the way for incredible projects that we see all around the world today.
Engineers at the Shard have taken this historic marvel to a whole new level. The first phase of the superstructure was tackled using some of the tallest and most powerful tower cranes in the UK.
They started with 4 cranes at ground level. Those went up to about 160 metres. But above that, we've still got 140 metres of the building to go. How do we get the structure, the construction equipment up to that height?
With the building now out of reach of the mighty tower cranes below, engineer John Parker and his team would take an unprecedented step, mounting a tower crane on the rising central core.
What was unique about the Shard was that the tower crane was supported on that slip form. Usually you have to fix the crane to the concrete. We avoided all that so they could both go up together.
As the hydraulic jacks pushed the core and crane higher, the machinery was kept stable against wind speeds in excess of 160 kilometers per hour by extending the lower section of the crane into one of the already cast lift shafts. But despite this ingenious technique, as construction reached unparalleled heights, engineers would have to adopt an even more radical approach.
They then had to use the crane that was attached to the slip form to build another crane which cantilevered off the main building and allowed them to build this final spire on the top of the structure.
This audacious solution elevated the machinery to a staggering 317 metres, the UK's highest ever crane, enabling engineers to lift custom-built steel sections to form the 23-storey spire.
The section could arrive on a truck, they could attach it to the crane, lift it up to the top, bolt it in place, and then get the hook back down to lift up the next section in 20 minutes.
As the tower's spire was completed, around 500 tons of steel had been installed in nearly 100 separate lifts.
The Shard was really going to hit the absolute limit of how high you could build in London.
With the building at its full height, designers could finally start to envisage the monumental Shard. The 40 floors of steel would house around 55,000 square meters of office space. For the hotel and residential accommodation above, concrete was specified for enhanced acoustics and to limit the building's sway. But as well as comfort, engineers had to guarantee the safety of thousands of people, potentially using the building at any one time.
We know from previous fires in tall buildings that it's a real challenge to get people out of the building safely, and that's an absolute focus for engineers working on tall buildings like this.
To ensure the Shard's inhabitants are protected in the event of fire, its designers would need to draw on another great innovation from the past. Professor Luke Bisbee is in Edinburgh, Scotland, as he looks to recreate an engineering marvel that changed the face of building safety around the world.
Now, it might be difficult for many of us today to recognize that fire was once a very serious and everyday threat to our homes and businesses. Heating and lighting were both largely reliant on open flame, and in combination with the fact that many of our buildings were made largely from wood, this is obviously not the best combination.
But in 1874, Connecticut businessman Henry Parmalee developed a system that would help to combat this threat of fire. With largely inefficient extinguishing methods, factories in many US cities were being burnt to the ground. As insurance costs rocketed, Parmalee was determined to control the premiums on his piano factory, so came up with an ingenious form of fire prevention.
So what we're going to do here is try to recreate a simplified version of Parmalee's invention. So what I'm going to do is I'm going to start a small fire here. Any fire in a building is a bad situation. And fires are particularly a problem in industrial buildings of the type that Parmalee was using, because if you have a localized fire such as this one, that fire can then spread to other flammable contents of the building.
During the night or even daytime shifts, many areas were left unattended, so human detection couldn't be relied on.
So the problem that Parmalee faced was, how do you detect a fire and then put that fire out if there's nobody around? So the solution that Parmalee came up with is actually here next to me. And the really critical piece is this little cap right here. And what I have here is a little metal valve, and on the underside of the valve, I have a secondary piece of metal, and we've attached that in this demonstration just with some wax. Now, Parmalee actually used a low temperature melting alloy. What I now have is essentially a valve on the bottom of this pipe that is temperature sensitive. And so the system that Parmalee had invented basically consisted of a reservoir of water. That reservoir is connected through a hole in its base to this copper pipe. That copper pipe runs across and down to the valve that Parmalee had created. And now let's see what happens when we introduce fire into our system. And as I do that, the valve gets warm, and the wax that is holding the plate in place should release the copper plate. And the valve almost instantaneously, sensitive to the temperature, releases water down onto my fire. And so what Parmalee had invented was really the world's first automatic fire suppression system that both detects and reacts to a fire very quickly.
Parmalee would name his innovation the automatic fire extinguisher. Following huge success in the US and Europe, his game-changing piece of engineering genius would pave the way for modern sprinkler systems around the world. engineers at the Shard have taken Parmalee's pioneering invention and supersized it, incorporating one of the UK's most advanced fire suppression systems.
The sprinkler system is all centrally controlled by a building management system. Total fire engineering control here, getting the water around the building to where the fire is likely to be.
Driven by 200 kilowatt motors, 2 megapumps feed water to 7 sprinkler zones. And 3 pumping stations are located at different levels to ensure even pressure for the building's hydrants. Access for the fire brigade is via 3 firefighting shafts, each including stairs and a fire lift that allows occupants to leave by the same means.
This is one of the first buildings where people can use the lifts rather than just the stairs when being evacuated in fires.
The Shard's safety systems may be cutting edge, but to complete this ultra-modern skyscraper, engineers still faced more challenges and would have to draw on another great innovation from the past.
Without Ellis, the glass-clad super towers of today, which dominate cities across the world, might not ever have been invented.
To produce more impossible engineering. The Shard in central London has rewritten the engineering rulebook. Boasting Western Europe's highest residence, its 95 stories are a mind-blowing sight for enthusiast Dr. Andrew Steele.
It's just incredible. It's this audacious piece of architecture, a splinter of crystal bursting out of the earth in amongst this rammed centre of London. All these different buildings, the Shard just towers above all of them.
And for fellow admirer David Knight, its iconic status is down to one material that appears to seamlessly emerge from the River Thames.
Look at the crazy amount of glass that this building uses. 11,000 separate pieces. It's extraordinary. It just extends above me in a great big ribbon of glass up to the sky.
To build this audacious structure required literally acres of glass, 56,000 square metres, which is equivalent to nearly 8 football fields.
But with little inherent strength, how do you create a tower of glass that's strong enough to stand up, even in the face of extreme weather conditions? This may not have been possible without the great innovators of the past. Engineer Dr. Rhys Morgan has come to the city of Liverpool in the UK to see a building which hides the secret of modern skyscraper design.
In the 19th century, as cities like Liverpool grew ever more dense and space for buildings became smaller, architects were faced with a real problem. They had to build upwards, but in doing so, they had to build thicker and thicker walls to support the increasing weight of their structures. So they needed a new engineering solution.
It was local architect Peter Ellis who would provide the answer, designing a new high-rise building using a revolutionary scheme.
This is the Oriel Chambers building, tucked away in Liverpool's financial district. And although a relatively unassuming building, it contains one of the world's most important engineering and architectural blueprints.
Completed in 1864, Ellis incorporated a state-of-the-art frame system, an iron skeleton, able to support the entire building. Ellis did away with the traditional method of building exterior supporting walls. Instead, his iron framework carried the load of the structure on the inside, allowing him to create a non-supporting facade on the outside.
Ellis's iron frame structure not only carried the weight and provided structural stability, but it also opened up a whole new world of architectural possibilities.
Now the walls could be thinner and lighter, and previously unimaginable amounts of glass could veil the building's exterior. Ellis had created the glass curtain wall.
In 1864, it was a really radical idea, and Ellis was criticised by his contemporaries for creating an architectural aberration.
The developers, however, saw the potential. The building's 56 road-facing bay windows over 5 floors flooded it with light, creating premium office space, and 150 years on, the benefits are clear.
It would have been a real luxury to work in here with the abundance of light coming in through these bay windows, or oriel windows as they're properly called. And to compare it with the building across the street, where the stone construction means the windows are very small, this would have been an amazing place to work in because of the light coming in from all directions. And he also didn't have to use electricity to use lighting in the winter time. A real advanced idea for the 19th century. The fact that these chambers were built in 1864, over 150 years ago, makes it one of the world's first examples of a glass curtain wall installed on a multi-storey office building. And to think that he was derided for it and was so far ahead of his time is quite extraordinary.
However, today it's said that his groundbreaking work on the chambers went on to inspire American architects responsible for the iconic skylines of Chicago and New York.
It's incredible to think that without Ellis's pioneering use of the curtain wall concept, the glass-clad super towers of today, which dominate cities across the world, might not ever have been invented. It's a real masterpiece of engineering.
Engineers at the Shard have built on Ellis's inspired architectural solution to create a standout structure. Its 13 acres of glass curtain walling cloak the entire tower.
What's incredible is that from outside the Shard, it looks like it's a structure made entirely of glass. But actually this glass takes none of the weight. That's all borne by the steel and the concrete structure inside. An incredible piece of engineering.
The steel and the concrete makes the building stand up. That provides the strength and the stiffness, stops it swaying about, supports all the loads. And one of the loads it supports is the weight of the cladding, the weight of the glass.
Unlike the rectangular oriel chambers, the Shard's extraordinary superstructure allowed its designers to hang 8 sloping facades, defined by the tower's iconic vertical fractures.
It's often called the Shard of Glass, and the idea was to have a beacon here that would shine out. And this sloping shape is very good at reflecting the sunlight and making it shine.
But creating a vision of glass on this scale called for extraordinary measures never before witnessed in the capital.
The steel superstructure of the building is enveloped by 11,000 panels of glass, each of them weighing 300 kilograms, and the only way to install them was for each of them to be installed individually by a specialist engineer. And looking at it from up here, you can see that's not a job for the faint-hearted.
In March 2012, the fitting of the final glass section would signify a huge milestone for the project.
It is good to be at the cutting edge and driving things forward and doing stuff that's never been done before.
This seemingly impossible architectural dream took less than 4 years from initial construction to its grand opening. The result of brilliant planning, design and testing by hundreds of engineers.
I'm personally excited because I see symbols of London that now include the Shard, It's very exciting to be involved with something like this. It's a one-off, it's a once-in-a-lifetime achievement.
By learning from the great pioneers of the past, adapting, upscaling, and making innovations of their own, engineers have changed the face of skyscraper design.
The Shard isn't just an amazing piece of engineering, but it's captured the public imagination to become a tourist attraction in its own right. And that surely is amongst its greatest achievements.
They have succeeded in making the impossible possible.
The engineers and architects who are involved in designing this building and the people that are involved in constructing it can rightly be proud of what they've achieved. It's an amazing structure.